here. All right, so as I mentioned during our last class meeting, homework number 10 is due, thank you, I'm glad you can hear me. Homework number 10 is going to be due on Monday, and normally our assignments are either due on Tuesday or Thursday immediately before class, but I wanted to give you a little bit of extra time for this, this next assignment. And so it's going to be due on Monday at noon. And then the following day, meaning 1 week from today, is when we're going to have the second midterm exam. And the format of the exam will be the same as the format for the first exam, where I release the test on Blackboard at 10:30 a.m. and then you have until 12:30 p.m. to take the test, meaning that you have a 2-hour window to take the exam. The length will be approximately the same, and so the only thing that will be different is that the coverage will be chapters 4, 5, and 6, rather than in our first test the coverage was chapters 2 and 3 of the book. So are there any questions related to the announcements before we begin? Okay, now in the class, I spend a lot of time working through examples, and I hope that those are useful. But most lectures also include a little bit of fundamental material, or some lecture in addition to the examples. But today is really just examples, and so I wanted to say a few things about how you can get the most out of a class meeting like today. And that is by actually working it yourself and getting out your calculator, getting a scratch piece of paper, and trying to figure out on your own, before I show it, how to interpret the problem statement, how to do the calculations, and how to solve for what's being asked. And so, it's good that you're in the class. It's better than if you weren't. And it's good if you watch the example. You'll learn more by watching the example than if you close your eyes and just listen. But the next step beyond that is solving the example on your own. And even if you don't get through it all the way and can't find the answer just from the problem statement and the given data, just the fact that you tried to engage that mental muscle is going to make you stronger. So that's just my long way of saying that as we go through 3 examples today, I hope really that you'll make an effort to, when I pause and stop talking for a few minutes, start crunching the numbers and try and solve these examples. So what you'll remember from last time is I said that there are 3 basic categories of momentum problems that we're going to be solving in Chapter 6. And broadly speaking, those problem types are the fluid jet problems, there's vane problems, and then nozzle and pipe problems. Today we're going to be talking about jet and vane problems, and then in Thursday's class we'll talk about nozzle problems and the additional complexity that they introduce. So today we've got 3 examples that are in the jet and vane area. In all of these, the same fundamental principle applies. And so just to refresh your memory about the momentum equation, this is the momentum equation as we're going to be using it for problem solving, and you can see that this is in the x direction. A very similar equation can be developed for momentum vertically, where you would just substitute in y in place of x. But the interpretation of the momentum equation is that we're trying to calculate the force required to hold the system steady. And so if you think about in all 3 of these cases, the fluid, because it's changing direction, is imparting a force to a stationary object. And then the equal and opposite reaction that's occurring is that this stationary object is imparting a force to the fluid. And that's what allows the fluid to change direction. And so taking, for instance, this jet of water that comes in and it interacts with the vane. It was moving only horizontally, and some force has to be pushing down in order to change its direction to now have some vertical component. And so what we're going to be calculating in problems like this is what force is required to prevent this solid object from sliding up and sliding to the right as it gets impacted by the jet. So if you think about what the jet would be doing to this object if it wasn't pinned to a support, let's just say that it's the vane itself with no support. So what would a jet of water do to that? It would cause this vane to move to the right, and then it would move it up. And so the force that we need to apply to hold the system steady, we can tell just by inspection, by our previous experience with the world, and just you've put your hand out the window, you know what way the force is. You know that the force you'd have to apply to hold this system steady is you're going to have to push down on the vane and to the left on the vane to counterbalance the forces that are imparted by the jet on the vane itself. So that's what we're going to be doing today, working through these three examples. And here's the first. So we have a fluid jet, and it's water, that is coming in at an angle, and it's filling a tank. And the tank is already partly full. The tank itself has a known mass of 5 kilograms. And then there's already a certain amount of water in the tank at this time, 20 liters of water. And by the way, I'm sure at this point you're already starting to think in terms of SI units, and you remember that the density of water is 1,000 kilograms per cubic meter, and also that there are 1,000 liters in a cubic meter. And so what that means is a liter of water has a mass of a kilogram. So here what we've got is we've got 20 kilograms of water in the tank that has a mass of 5 kilograms. And what we want to find out is, because of this fluid jet coming in, that's going to cause a reaction against the stop block to the left. If this stop block wasn't there, it's possible that the tank would start sliding to the left. And so what we want to know is the force that the stop block applies to the tank. And so you can see that I've put in bold here just to draw your attention to that there is an equal and opposite reaction occurring. And what we don't want to know, we aren't asking in this problem, what's the force of the jet on the stop block, but rather we're asking what's the force of the stop block on the tank. And that is the force that you'll calculate with this equation, because the stop block is applying the force required to hold the system steady. So on the previous slide, I circled the left side of this equation, and I said what this is, the interpretation of this is, quote, the force required to hold the system steady. And the stop block is applying that force. And Eric asks if the sum of the forces are 0 here, and they are, yes. It's stationary, and we'll assume that the stop block is causing this, it's preventing it from moving at all. It puts the stop into stop block. So then the second component of what we're going to try and calculate is the vertical forces. And so the vertical forces are going to include 1, the force associated with the tank's mass, 2, the force associated with the water that's already in the tank, and then 3, the force of the jet impacting the system. And so we'll apply the same equation in the y direction, and we're going to find out what is the force that the jet applies to the system that it's entering. Okay, so I'm going to pause and let you calculate, but before I do, I'll give you a couple of suggestions on what to calculate first. And so if we look at the momentum equation, what we know is that we're going to need a mass flow rate, and then we're going to need to know the velocity in a certain direction. So up here in the equation, on the right-hand side, we need to know the mass flow rate out. And so envision drawing a control surface that surrounds and encompasses the tank. That's our control surface through which the jet is flowing. And there's no stream going out. This is a tank that's filling, and so there's only an in for for this problem. So the entire first term of the equation is going to drop out. It can be canceled to 0. And so we do have a mass flow rate in that you're going to need to determine based on the given diameter of the jet and the velocity of the jet. Okay, so calculate as a first step the mass flow rate. And then the other thing that's a little bit tricky is finding what is the component of the velocity in the x direction. So here the angle is specified as 70 degrees. And so that means the velocity that's coming in, 15 meters per second, most of that velocity is vertical. Less of that velocity is in the horizontal direction. And so you're going to need to find the cosine of 70 to tell you what component of the velocity is in the x direction. And then the sine of 70 would give you the component of the velocity that's in the y direction. Okay, so those are all of the guiding points and initial hints that I'm going to give you for now. But my suggestion is first find the sum of the forces in x. So find the momentum in the x direction, because that's what this first bullet point is asking for. And then in the y direction, you'll have to also account for the masses. Provide some of the calculations that we're going to use in other spots as well. Let me pull some of those up and see if the same things occurred to you. Because even if you don't know exactly how to solve every part of a problem, for instance, if you're given the diameter of a jet, you probably aren't wasting your time if you calculate its cross-sectional area. And so that's one of the initial things that I've done. You can see is with the given diameter of the jet, the diameter was specified as 30 millimeters. So that's 0.03 meters. And then calculated the area of the jet. Similarly, if you're given the mass of the tank, and this is a problem all about forces, then converting the given mass of the tank over to its weight is going to be a reasonable thing to do up top. And so the mass of 5 kilograms multiplied by g will tell us the weight of the tank in newtons. And likewise with the water, we had a volume of 20 liters, and so that's going to be 0.02 cubic meters. So did the volume conversion here, then the mass conversion is 1 kilogram per liter, and then from mass to weight by multiplying it by g. So we have both the weight of the tank and the weight of the water. And then you can also see the mass flow rate that I determined for the x, well, it's not just the x direction, by the way. The mass flow rate's the same whether we're working in the x direction or the y direction, because mass flow rate is a scalar. It just has magnitude. It does not have direction. Whereas velocity is a vector, and it does have magnitude and direction. So the mass flow rate is not specific to whether we're working in x or y. But let me pause here and let you continue, and what I'd like you to type into the chat box, if you've got it, is what is the force in the x direction? So what force is required to hold the system steady? Okay, so let's take a look at how we get the force in the x direction. Let me scroll down a bit here and we'll talk through it together. So in the x direction, the jet is moving to the left. So when we put the velocity in, we're going to need to have the minus sign for the jet velocity, because it's moving from the right to the left, which is the opposite of our positive direction. Our positive direction is from the left to the right. So you can see that I've simplified the overall momentum equation for x because there's no mass flow out. there's only the mass flow in. So there's minus the mass flow rate in times the velocity, and then cosine of 70 because it's only a fraction of the velocity is in the x direction. So what fraction? 34.2%. If you calculate the cosine of 70, then that tells you it's only going to be a small portion of the jet's velocity that's in the x direction. And you'll note that I have the minus sign for the velocity because the jet's moving to the left, but then there's no sign associated with the mass flow rate. And also, we don't have to apply the angle to the mass flow rate. You only apply that angle one time, and that's with the velocity. So the two minus signs cancel out, and we get that the force is 54.4 newtons acting, that's the force of the block on the tank. So the force required to hold the system steady is to the right. So both the fact that it's a positive number and below that I've also indicated to the right lets us know that the block is going to be pushing on the tank to the right direction with 54.4 newtons. So any questions about that first part? Okay, now in the y direction, if we go back here, things are a little bit more complicated. So what's acting on the bottom of the tank? So that is this floor or countertop or whatever the tank is on. It's pushing up on the tank. We know it's pushing up because it has to support the weight of the tank, has to support the weight of the water in the tank, and also it's reacting against the jet that's coming in. So just kind of, in our minds, instinctively, by inspection, we know that the force is acting up, but we want to know what's the magnitude of it. So it's going to be the combination of those three factors: the mass of the tank, the mass of the water, and the weights that they produce, and then also the effect of the jet. And so if we go back and look at this momentum equation in the x direction, in y, the sum of the forces in y, it's going to be kind of similar how we set it up because there isn't going to be any outflow term. And so the overall equation, we're just exchange x for y. So sum of the forces in y is equal to the mass flow rate out, velocity out in y, minus mass flow rate in, velocity in y. But there is no mass flow rate out. So we cancel that entire first term, and if there is no flow out, then it's just going to be the mass flow rate in, which is the same. It's the same 10.6 kilograms per second. The difference being that now for the velocity in, it's going to be not the cosine of 70, but the sine of 70. All right, so I'll pause for a second here, give you a chance to find the overall force. What it's asking is not just for the force required to hold the system steady, but what's the overall force acting on the bottom of the tank. So it's going to be the sum of the jet impact force plus the tank mass and the weight of the water. Type it in the chat box when you think you've got it. Okay, so Caleb got this one. Let's take a look. First of all, the jet impact force we can calculate with the momentum equation. As we already talked about, there's no flow out, so the equation just simplifies to the minus, because we always subtract the inflow term, mass flow rate in, and then the velocity component in the in direction vertically. So for us, it's still going to be that negative 15 meters per second because it's down. Remember, the minus sign isn't simply because it was minus before. Here, it was minus because it was to the left. In this case, it's minus because now we're in the perspective of vertical. And in this case, it's minus because the jet in the vertical direction is acting downward. So it's still minus 15, but for a different reason. And then the component of the velocity that is vertical, 0.9397. That's the sine of 70. So when we calculate the force, it's a positive number because the two minus signs cancel each other. And that indicates the force required to hold the system steady is an upward force. And so then the total force that we need to calculate here, the force that is acting on the bottom of the tank, is the weight, the momentum force, and total it's 394.6 newtons. So are there any questions about that example? I think you're going to find that the homework assignment is pretty closely related to these examples, and so I hope that this initial familiarization pays off in making it a little bit easier to solve these problems. The next problem I'd want to show you is related to a jet that passes through an orifice. And so what we're looking at is a side view, and in this side view, a circular water jet is flowing from the left to the right, and it's in contact with the air. And I say that simply just to draw your attention to the fact that this water jet is not pressurized at all. On Thursday's class, we're going to be talking about moving water that is inside of a pipe and is pressurized. And things are a little bit different when the fluid is pressurized. But in this case, it's not. It's just an open to the atmosphere contact jet. And its velocity is 90 meters per second, both before and after this orifice. And so what the orifice is really doing is that some of the stream that was moving horizontally is now moving vertically. And what we're looking at is a cross-sectional view, and so it's not like that there's two outflow. It's kind of like fanning out. And so it was a circle jet, and then it's spraying in all directions this portion that couldn't fit through the orifice. And so big D is before the jet passed through the orifice, and then the little d, 3.5 centimeters, is the diameter of the outflow jet. And so what we're going to calculate here is just the force required to hold the system steady, and then from that, look at what it's asking. It's saying, what external force does the jet apply to the plate? And so when we calculate this force, you'll get the force required to hold the system steady, and then you always need to carefully consider what the question is actually asking, because it may be asking you to determine the equal and opposite reaction, and in this case it is. And so here we need to calculate, you'll calculate the sum of the forces in X, and then the opposite of that is the water force acting on the plate. All right, so first things first, calculate the mass flow rate. This one's a little bit easier because we don't have to deal with an angle at all. You're just calculating the mass flow rate, and you can do that by determining the cross-sectional areas. And so maybe I should have started with this one because it's a little bit easier than the one we just solved. But in any case, I'll pause for a moment and give you a chance to calculate. And if you do have a guess in the chat box, be sure that you mention not only the magnitude of the force but also its direction, because in problems like this you need to have both to be fully correct. Okay, during the setup I didn't necessarily refer to the control surfaces, and so maybe it will be useful if I just draw the control surfaces that you could apply in a problem like this. And so I'm drawing a box. I'll have to make it translucent here in just a second. I'll fill it with nothing and make the line dashed. just because that's what we usually do. All right, so in the x direction, there's flow going in and flow going out. And because there's going to be less flow going out than was going in, then that means that there has to be a force required to hold the system steady. In other words, think about all of the water that was moving to the right, and now its direction has been changed vertically. So we should kind of just instinctively know that you're going to have to push to the left to support that reaction that's occurring, to hold the system steady so that this fluid jet interacting with the plate doesn't cause the plate to move to the right. We have to apply an external force to the left. So the mass flow rate out is going to be less than the mass flow rate in. David already correctly identified that the mass flow rate in is 706.9 kilograms per second. Let me show you the calculations that lead to that. All right. So if you're ever stuck on problems like this, if you're given a diameter, chances are you're going to need a cross-sectional area. If it's a circular jet like this, then the area is pi d squared divided by 4. So you can find the cross-sectional area of the jet that's coming in, the cross-sectional area of the jet that's going out, and then the mass flow rate in, 706.9 kilograms per second, because we're just multiplying the density by the cross-sectional area and the velocity, and then the out. It's the same approach, just a smaller area. So there's only 86.59 kilograms per second going out. Now, where's all the rest of the water? Well, it's been redirected vertically. So it's not that there's any fluid that's accumulating inside of the control volume. It's just that the water is going in a different direction now. So to calculate the force, we're going to put the out mass flow rate that we just calculated, and then the velocity out is 90 meters per second. Same as the velocity in is 90 meters per second. So to find the sum of the forces, here you can see it's the out mass flow rate and the out velocity, and that's positive because it's to the right, and there's no sine or cosine required because the jet was moving entirely in the x direction, and then minus the mass flow rate in and the velocity in. And so what this is saying is that you have to push, because of the minus sign, you have to push to the left to hold the system steady. And the question itself is asking is, what force does the jet apply to the plate? So that's the equal and opposite of what force external is required to hold the system steady. So here, because it's asked from that perspective of the force being imparted by the fluid on the plate, then it's a positive. So you'll notice now I'm expressing it in terms of kilonewtons, and then I've also clarified there in parentheses that we're talking about a force that's to the right. The jet's pushing on the plate rightward. Are there any questions about that second example? Okay, well then the last one we're going to look at today is a vane that's redirecting the flow. And if we just take a look at what's happening here, the jet comes in the x direction with a given mass flow rate, 6.7 kilograms per second, and then a given velocity of 11.5 meters per second. Now, in the earlier example that we just worked with that orifice that part of the jet was passing through, in that problem it was said that the velocity was the same in and out. Here, what we're assuming is that interacting with this vane has slowed down the magnitude of the velocity, because what you'll notice is that V2 and V3 are less than they were that velocity that was coming in. So it's slowed down a bit. Now we're going to have to apply the continuity relationship here because you're given the mass flow rate in, but you're not told how much of that mass flow rate is going into stream 2 and how much of it is going into stream 3. So when I say you have to apply the continuity equation, do you remember what equation I mean? Like, what is the continuity principle? Anyone in the chat box or with the microphone? What is the continuity equation? Jeremy's got it. He says A1V1 equals A2V2. And that's true if there's only 2 fluid streams, as we've seen before. But now here, there are 3 fluid streams. So, Jeremy, how would you, in this case, adapt what you just wrote in the chat box to this particular scenario? Because in this case, there's A1V1 would not equal A2V2. But I mean, I get what you mean. You were saying flow in equals flow out. And that's the overall principle that, yes, still applies here. What we're saying is that there's no fluid accumulation in the control volume. So what flows in must equal what flows out. But as you can see, it's flowing out in 2 locations. And so what would be the revised equation? Would the V out be the sum of V2 and V3? No, it would not. But what we would say is that Q in equals Q out. So Q1 equals Q2 plus Q3. That would be one way to say it. Courtney's got it. Courtney says A1V1 equals A2V2 plus A3V3, and that's exactly right. Excellent. Now, remember, in momentum problems, we have to go one step further. And rather than expressing things on a volumetric basis, in momentum problems, we are looking at it on a mass flow basis. And so then what that would mean is m dot 1 equals m dot 2 plus m dot 3. So in other words, I had said earlier, Q1 equals Q2 plus Q3. Well, if it's the momentum that we're talking about and mass flow rate, m dot 1 equals m dot 2 plus m dot 3. All right, so here it's asking, what forces does the water jet apply to the deflection plate? And so think about the momentum equation. The momentum equation is asking you what force is required to hold the system steady. But this is another one of these problems where it's actually asking the equal and opposite of that. And so this particular, the way they phrase this one is, what is the force of the jet on the plate? Okay, so what I would like you to do, my suggestions for how to tackle this is, first of all, deal with continuity. And so what we want to know is m dot 1 is given. What is m dot 2 and m dot 3? So in other words, solve for m dot 3 because you're given the diameter, and we'll assume a circular jet. So with the diameter given here at 3 and velocity at 3 given, then you can calculate m dot 3. And then if you know m dot 1 and m dot 3, you can calculate m dot 2. So let's just get to that point and not go, well, I mean, you can go further if you want, but I'll interject after you have some time to calculate and type into the chat box, what is m dot 3 and what is m dot 2? Okay, so there's a lot going on with this one, and from the given diameter of the jet here at 3, you can get the cross-sectional area, and then from the cross-sectional area and with the velocity that's given and knowing the density of water, you can get the mass flow rate at 3. So then by continuity, which says that whatever came in at 1 and didn't go out at 3 has to be going out at 2. So that's M2 is equal to M1 minus M3. So that means that the mass flow rate at 2 is 3.59 kilograms per second. Okay, so now what we have to think about for the rest of this is in terms of our two directions. In this case, we're going to be solving both for the force in X and for the force in Y. So I suggest that we could start with the X direction. So the flow that's coming in has an X component, and the flow that's coming out also has an X component. And in fact, there's more than one stream that's going to be going out. And so in this equation, where it says the sum of mass flow rate out, velocity out, what that means is that we can have more than one term for this outflow component of the momentum equation. And so let me just show you how I set that up, and then I'll leave you to start substituting the numbers in. Okay, so working in the X direction, the in is all in X, but in the out, we only have a component of its given velocity. So we're going to have to make use of this 70-degree angle that's specified. Okay, so the overall momentum equation, which we've seen before, expands out to have more than one term for the outflow. So you can see what I said is that it's the mass flow rate at 2, which is this stream at the top, multiplied by the velocity at 2 and the cosine of the angle, because the cosine of the angle is what's going to give us the component of the velocity in the X direction. And since it's changing its direction 70 degrees, that means more of the velocity is going to be vertical than will be horizontal. And then adding this term for the stream at 3. Now, the stream at 3 is to the left, and so we just need to pay special attention that when we substitute in the magnitude of the velocity at 3, that we use minus 9.9 meters per second, because it's moving in the opposite direction than our standard rightward convention. And then finally, the last term that will be in this equation is subtracting out the mass flow rate at 1 multiplied by the velocity at 1. Okay, so I'll pause for a second, give you a chance to use that calculator, use the pencil and paper, and try and calculate what is the overall force required to hold the system steady in the X direction, first of all, and then the equal and opposite of that will tell you what force is being applied by the jet to the vane. All right, well, let's take a look at the substitutions here. Okay, so the mass flow rate at 2 we had previously calculated through continuity equation, by subtracting 3 from 1 is what gave us 2, and then the given velocity at 2 is to the right. That's the outflow that's going up and to the right. So it's got positive 10.8 meters per second, and then we get the component of that velocity that's in the X direction by multiplying by the cosine of 70. Because it's not all horizontal. Since it's been deflected, a good amount of that velocity is going to be in the vertical direction. Okay, so that's our first component of the outflow. The other outflow, this stream 3, is going to be the mass flow rate of 3.11 kilograms per second, and then you'll see the velocity is minus So that minus sign is because that stream is moving to the left in the x direction, and the cosine of 70 is also going to give us the horizontal component. And then finally we subtract out the inflow term, and so all of that inflow jet was horizontal, so we don't need to use any kind of an angle. It's just going to be minus 6.7 kilograms per second times the 11.5 meters per second velocity. So you can see below that I'm just kind of combining terms together where I'm finding the force after multiplying the mass flow rate and the velocity together, and then the component of that force that's acting in the x direction. And so it's negative 74.32 newtons would be the force required to hold the system steady. So based on what's happening, that jet is applying a force such that the external force required to hold this deflection plate steady, we would need to push to the left to hold it steady. So, but then what this is asking is what's the force of the water jet on the plate? And that force is to the right. So then down here in the solution, the force of the jet on the plate is 74.32 newtons to the right. So it's the equal and opposite of the force required to hold the system steady. Are there any questions about how we solve for that force in the x direction? All right, the approach in the y direction is similar, except for that there was no inflow term in the y direction. There's only an outflow. So the sum of the forces required to hold the system steady is going to be the mass flow rate out multiplied by the velocity out in y. And we have two terms there because stream 3 has a positive velocity because it's going up in terms of y, and then stream 3, the one shooting down, is going to have a minus sign associated with its velocity. And so you can see the substitutions are going to be that we have the mass flow rate at 2 multiplied by the velocity out in y at 2, and so that was the stream that's moving up and to the right, and so vertically that's positive, and so there's no negative sign there. And now the angle that we're using is the sine of 70, because that will tell you the component of the velocity that's vertical. And then the similar thing for stream 3, except that the velocity is minus because it's down, and then the net difference between the two is 7.5 newtons. So that's the force required to hold the system steady, and then the force of the jet on the plate is equal and opposite to that. It's negative 7.5 newtons, and so that means that the jet is going to be pushing the plate down. And let's just see, like, how could we have known that instinctively, that the jet is going to be pushing the plate down? And the reason why is because there's more of the water going through stream 3 than there is going through stream 2. So that's why the force is down on that plate. Okay, well, that's 3 different examples for you to draw from as you work on this next homework assignment. Just as a reminder of where things go from here, that assignment is due on Monday the 18th. Is that right? That couldn't be right, right? I need to update that. I'm surprised you didn't catch it and correct it, because you guys are usually pretty good about correcting my many oversights and mistakes. Yeah, that should be the 16th of November. So Monday is the 16th, not the 18th. So Monday the 16th at noon is when homework 10 is due, and then we'll have the exam the following day. So that's it for today. I hope you have a good one, and I will see you either in the lab or in class on Thursday.